Today we're going to discuss the fundamental theorem of line integrals. Okay, so let's recall what a line integral is again. In general, we think of a vector field x, y, and if you want, you can put a z in there as well. But we'll just do a two-dimensional one. It's easier to draw, like that. All right, and we can draw it in some region of two-dimensional space. And you can think of it as everywhere in the plane there is some vector. There's some vector that's defined, like this. Okay, so and then what we're going to do then is take some point. We'll call that point 1, which will be x1, y1. And there'll be some path that we have going through to what we'll call point 2. And that's going to be equal to x2, y2. All right, so we can parameterize this path by a function, a vector function r of t, that makes the path, we'll call path c, and it's from t equals a to t equals b. All right, and so we've learned before that we want to compute the line integral on this thing. So if we want to compute, so that to compute the integral over the path c of our function dotted to the direction we're headed times a small path length right there. We also learned that we can write this as the integral from a to b once we have our parameterization of f. I'm going to define this. I'm going to define r here just a little bit more precisely as the vector function x of t, y of t. And that's going to be of x of t, y of t, dotted with r prime dt. Okay. So again, r prime will be x prime, y prime, where the derivative is in dt. Recall, though, that r prime, the vector r prime, is dr dt. It's the derivative of this vector function. And so we can rewrite, notationally, we can rewrite r prime dt as equal to what we'll call dr. And so a third representation of our line integrals is to write it as integral over the path c of f dotted with dr, where now our differential is a vector differential. And that's just a different way to write the same integral. And typically these are construed as a way to calculate work. Okay, so work is a form of energy, so you're pushing some particle or a charge or some mass through a gravitational or electric field, and each point you have to you move some small path element ds forward, and you have to work against some force field. And so this is the way to calculate that. All right, so now we're going to talk about what this fundamental theorem is. And so we're going to invoke what we know about the fundamental theorem of calculus. Okay, recall that if I have a function g prime of t, and it's integrable, so we can write it as, so if I want to take the integral of g prime dt, I know that I can find the antiderivative, that this is going to be g at b minus g at a. Sometimes they call this the net change theorem. and then and that g prime, of course, is the instantaneous or the incremental change, or the slope of the function g over small little increments of time. And so if you add up all of those little changes times a small increment of time, you'll get some net change, which is the difference between where we started here from where we're going to end up, from A to B. All right, so that's what we call the fundamental theorem of calculus often. So let's see if we can expand on this notion and see if we can find a similar. So is there an analog for line integrals? And yes, there is. And it is exactly the net change theorem, but just written in a slightly different way. So let's look again at our function. We had this vector function, and we are going to define it at, we're going to evaluate the vector function on this path C, and we were going to dot it with another function, another smooth function, r prime of t. Or we can also write this as f evaluated at the vector r of t dotted with r prime of t. All right. Okay, and so then, of course, the integral we wanted to compute was a to b f x of t y of t dotted with what I'm going to call, so r prime, of course, was x prime of t y prime of t dt. Okay, so there we go. But now let's recall the chain rule. So the chain rule states that if we can find a function, let's say we have a function f of x of t, y of t. Right, so this is lowercase f. It's a different function than our capital F up here. If I want to take its derivative, and we have it's a function of two variables, but we've yoked both variables to a hidden parameter t, or an inner parameter t. We know that that becomes the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. Okay, so if we look a little carefuler here now, and so we know then if I have an integral from a to b of such function, the derivative of this function, f of x of t y of t dt, then I can use this net change theorem to essentially anti-differentiate. So we have f at x and y both evaluated at b minus, hold on, I'm just going to do a little erasing here. There we go. Minus f evaluated at a. Okay, and that is simply just a rehash of the net change theorem, or the fundamental theorem of calculus, right there. Okay, so we have a function and it has its derivative, and we want to integrate this function which is a derivative, and when we integrate it, we simply evaluate it at the ending point and subtract the evaluation at the beginning point. All right, but now let's pause to see what this looks like. I'm going to rewrite this a bit more. So we have a to b, and this becomes, if we look at this again, this becomes the vector of partial f x, partial f y, dotted with, well, hold on, let me just rewrite this. That's going to be the vector partial f x, partial f y, dotted with the vector x prime y prime. Of course, so we can rewrite this at, and of course x prime y prime is exactly r prime of t dotted with this vector function. So if f is equal to the vector function partial little f of x and partial little f of y for some f, then we can write this as, and that of course is the gradient of this function. So we're saying then that's equal to the gradient of f dotted with r prime dt. All right. So we can rewrite this again, that if we have some pathway, we're going to write it like that, gradient of f dr. All right. So we're saying then if our vector function in question that we were wanting to study is a gradient field, i.e. that the vector function is produced as the gradient of some scalar function where f, x, y, and it could be a z if we want to talk about 3 dimensions, is some function from R2 to R. All right, then the following is true. We can simply evaluate the function at the endpoint, call it P2, minus the beginning point, P1, of our curve, C. So this we can write down as a theorem. So again, if we can find some function little f where if we take its gradient like that, and that produces this vector field, and that is true for every point along our path, then to compute the line integral, we don't have to do a full calculation. We simply find the little f, and we evaluate it at the ending point and subtract it from the value of f at the beginning point, and that will equal the work done. That will be our integral. So let's talk about an example. Let's talk about we'll talk about a gravitational field, say. So if we have a gravitational field, remember gravitation. So we have some force, a vector force, x, y, and z. Right? We'll do this in 3D, and that's going to be equal to. We usually write it like this: x, the vector, to the third power, all over the gravitational constant times a little mass times a different mass, which we usually think of as a big mass. We multiply by the vector itself. We put a minus sign. So the idea here is we have a big mass that's sitting at the origin, and we think of it as a vector here going out to the position of the little mass, right? And so at that point, there is a force that's pushing back that's proportional to this constant here, but it's in the direction, the negative direction of the position of our little mass. Okay, so so that's nice. So if we want to talk about just the actual, so let's rewrite this a little bit. So this actually turns out to be little g minus little g times m times big M times, so what is this down there? That's going to be the 3/2 root of x squared plus y squared plus z squared, right? All times, and here's the vector part. It's going to be an x and a y and a z. That's the vector part, because that is exactly the vector x, y, and z. Right there. All right, so again, this is the scalar multiplication that goes out in front, and this is what imparts it with an orientation or a direction that it's pointing in. Okay, so so the question then is there? So in order to use the fundamental theorem of line integrals, we must find an f of x, y, and z such that the gradient of f is equal to our capital F. Okay, so can we find that? Well, it's pretty straightforward. If you look at this and you do an antiderivative in any of the variables, that we can find that f of x comma y comma z is equal to the function 1 over the magnitude of x. So this is, we can rewrite this. Remember, this is a scalar function. There's not a vector here. This is a scalar function. And that's going to be the square root of 1 over the square root of x squared plus y squared plus z squared. Okay? So that's, of course, we have to put our little g, our little m, and our big M there. So little g, little m, and big M, just like before. Okay, so that's all nice. Here we go. So can this work? Well, I could take a derivative just to see here. So I'll just try doing just the partial with respect to x, and that'll of course be negative g little m big M, and then that was a 1/2. That was a negative 1/2 power sitting there, so that becomes a x squared plus y squared plus z squared times that becomes a 3/2 power, and then there's a 2 down there, and then we have to do the chain rule, so we do the inside, that becomes a 2x, so the 2's cancel, and it produces exactly the first component up there. So there's a minus, here's the scalar, here's the other constant that is divided by, and there's an x. And so you could do the same for y. You would just have to put a y there instead, and the same thing for the z variable. You would just have a z in the top instead of an x. Okay, so there we go. We now know that the potential function then, we'll call this the potential. The potential function f is equal to g m capital M over the length of our vector. So it truly is just the distance between the masses. So we're saying that the gravitational potential then is going to be between these two masses will be inversely related to the distance between the two masses. So that's what we're saying. All right, so now let's talk about a problem. Let's say, I'm going to say we'll go in the plane. We have a path from, we'll say 1, 2, comma 0, right? Because we're going to say that z is equal to 0 here. And we're going to go to the point 3, 4, comma 0. So I'll just draw that out. So we'll start at 1, 2. And we're going to have some path that goes to 3, 4. All right, we'll call that path C. So the integral from C, of C, times the gradient field, which is the gravitational field now, dr of that path, we simply have to evaluate f at the 2 points. So we need to evaluate it at point 1. So point 1 is, so we have to evaluate it at point 2 first. So that's going to be f at point 2 minus f at point 1. And that's going to be 1 over square root of, we have to put a 1 in there and a 2 in there, and that gives us a 5. And then, sorry, no, we have to put a 3 and a 4 in there, so that becomes a 12. Sorry, minus 1 over root 5. So that's the answer. So all we have to do is evaluate at the endpoints, and that's nice. So of course we have to remember that the gradient field, this has to be true for every point. On C. Okay, so in later lectures we'll talk about more details of the fundamental theorem of line integrals. But now we have a really nice result, a really nice convenient result that helps us compute line integrals. in space. Thank you very much.